Hello guys, my name is Al.Mahdi and I'm talking today about the shift register thingy from the assignment. I'm going to talk about digital system design. We have this assignment which is called design a linear feedback shift register LFSR in another way, which cycles through the following stage from 001, 011, 111, 110, 101, 010 and 100, and he said that the LFSR, which is the linear feedback shift register, could be set to initial state of 000. Okay, that's obvious. Okay, with an active low asynchronous set signal, meaning we have an active low set signal. If you remember the D flip-flop, let me just do this. If you remember the D flip-flop, we have a synchronous, which is this, and it relates to the clock or something like that. So this is the clock signal, and if it's a synchronous, then we're gonna have some label like this. Meaning if you do the rising underscore edge, then you pass the clock, isn't it? You do the if statement for the reset. For this example, this is the reset. If it's equal to 1, then it's gonna have its own activation or wherever. It's gonna reset the D flip-flop to 0, since we are dealing with this reset over here. Anyways, this is I'm talking about here about the synchronous. When it comes to asynchronous, you do the if statement before the clock. So basically you're gonna do the if r is equal to 1, then the q is gonna equal to 0, else if the rising edge of the clock do wherever. Okay, do wherever here. Maybe q is equal to d. Usually this is the D flip-flop. Then end f statement, and here, this is this is representing a D flip-flop with a reset, asynchronous reset, and input as a D with a clock of rising edge, and Q, which is the output. So this under the process method, if you can say process, and you're gonna have the clock over here, and you're gonna need to also add the reset. So basically we gonna have process, inside the process, which is the sensitive list. You're gonna have the clock, and you're gonna have the reset. Anyways, so this is the asynchronous thing. Now we're not talking about the D flip-flop anymore. We are talking about the register. Well, what is the difference? It's the input and the output. The register, you're gonna have the D as a lot of inputs, and the outputs is gonna be a lot of outputs, meaning that the D and the Q are going to be vectors with a specific range. So let's say from 2 down to 0 gives you 3 bits. Okay, 1 second, I'm gonna pause to plug in the power. Alright, I'm back. So I was talking about the vector. The output is gonna be vector, and the input is gonna be vector. Well, we're talking about register, so let's go ahead and clear this up. If we're talking about register, the idea of register, let's say you have an input signal, okay? You want to represent the data as a parallel data instead of sequential data. This is D1, D2, and this is the D3. This is the data. Basically, you're gonna store the this is gonna be inputted, okay, and so on. this one gonna be inputted, and it's gonna be shifted to over here. It's gonna be over here, then shifted to over here. So when it enters, is gonna enter from only one input, and it's gonna give you 3 outputs signal. So basically this is a 3-bit shift register. Alright, so because we have 3 D flip-flops, or let's say flip-flops, because you can also do it using toggle or toggle, or what do you call it, JK flip-flop. So anyways, well, we're gonna stick with the D flip-flops because it's the simplest. Anyways, let's just clear this up, and I'm gonna go ahead and do a simple explanation of what is the shift register, what is the linear feedback shift register. Alright, what is that? Basically, if you understand what is the shift register already, it always shifted the data from either right to left or left to right. It depends on where's the input. Alright, so each of these have an output, right? Let's assume that initially we have 1. Alright, so the feedback part, what does that mean? Basically, the linearly feedback part is an XOR gate. Okay, you just connect 2 inputs from either flip-flops, then do reconnect it to the first one as a feedback. Basically, if you don't connect anything as a feedback, then it's gonna be static. Right now we have a feedback signal where it comes from a linear equation, which is the XOR, and we're gonna have something like this. If you know the XOR truth table is like 0 0 0 1 1 0 1 1, the output is gonna be 0 if they're the same. If they're different, it's gonna be 1. So since those are the same, so the output is gonna be 0. So the first bit is gonna be 0. All right, then this is gonna be shifted, and that is gonna be shifted. So it's gonna be 1 1. So this is the first value we are gonna having. You're gonna be having. So you're gonna be having a 0 1 1. All right. So you have a 0 1 1. If you want to do it again, let's assume you still have this connected. So you're gonna have still 1 1. So you're gonna have 0. Okay, and these are gonna be shifted again. So we're gonna have 0 1. All right, so on. It's gonna be cycling until it reaches a value where it goes back to the same value, which is 1 1 1. Anyways, now since we got the idea how does the counter works using the using the shift register, so you're gonna have a special simple way of designing it. So from the question here, if you go to the question over here, it says that it wants to be cycled from 0 0 until 100. You can see the values. So basically, if we just do a simple state table, if you don't know what is the state table, is basically you do like divide the table, say this is the current state, okay, this is the next state. For the current state, we're gonna start with 1 1 1 as an initial value, right? Then from 1 1 1 we're gonna go to 1 1 0, right? 1 1 0. From 1 1 0 you're gonna go to, from 110 you're gonna go to 101. From 101, this is the current state, we're gonna go to 010, just write it out. And then from 010 is gonna go to the 100, 100, and from 100 it's gonna go to 011. From 011 it's gonna go back to 111. So basically this is the state table, and you can label this as a Q1, Q2, Q3, and this is Q plus 3 and Q plus 2 and Q plus 1. And to do so, because we have three bits, since we have 3 bits, you're gonna have 3 flip-flops. It doesn't matter what type of flip-flop, but you should stick with the easiest, which is the D flip-flop, recommended. To do the D flip-flop, you just connect them like so. This is the D. Well, if you don't get why we connect them, you can do the K map. From the K map, you can know why we connect this directly to that one based on this truth table. But it depends whether this and that goes back to the feedback, or this and that, or that and this. So we are going to do the K map as for each Q plus. So each Q plus is going to have a K map. So Q3, Q2 plus, and Q1 plus. You're going to have a simple K map, and you're going to have the outputs. For me, I already got for Q plus 1, I got Q2, and for Q plus 2 I got Q3, and for Q plus 3 I got Q1 XORed with Q3. Okay, so you see this, let's say this is Q3 plus, Q2 plus, Q1 plus. Then I'm gonna have something similar to this, XORed, and go back to this. Oops. Let's go back to this. Yep. So it's gonna be like something like that. Anyways, this output is gonna come here. It's gonna be something like this. Q1 XORed with Q2 is gonna go ahead to Q plus. So it's going to be something like that. You're going to have the diagram. Also, from the question, it said you have a set low, and you're going to have this as set as a low because we have the bubbles. So you just connect them all together. You have the set signal. So we are done with the diagram. Right here. I mean the logical diagram. And let's go ahead and just use simple diagrams to explain how this would work. So from 111, which is initially starts from here, then is gonna go to simply since mine is like Q plus first, then Q1 the last is going to be a little bit opposite, so it's going to be in a different way. So they have a Q plus. Okay, so it's going to go from 111 to 011 to 101 to 010. From 010 is gonna go to 001. From 001 is gonna go to 100. From 100 is gonna go to 110, and then back to 111. So this is the the diagram for this time diagram. State diagram, sorry, this is the state diagram. State diagram. Okay, so basically it's just to simplify how will the device work. Now we finished the theory part, or the designing part. We need to do the coding. So we have done that. We need to do the code part. VHDL. Alright, so let's go ahead and do this right now. Okay, I'm just gonna do it quickly. It's quite simple to do. First, go ahead and open ModelSim. Alright, I'm gonna have a new project. Create new project. New project. Yes, I'm gonna save it on, yeah, here. I'm gonna name it Q1 point. Oops, sorry. I didn't want to wait. New project. Q1.1. Just create it. Create new file. I'm gonna name this as an linear feedback shift register. Okay, I'm gonna just do the test bench over here. Linear feedback shift register underscore test bench. I'm gonna press OK. Now I have two files. Now when I double click, you're gonna see something different appears, but it's okay. It's my editor. It's different than yours, but it's alright. Okay, first thing to do is library. Include the library, which is IEEE. I'm gonna just do a comment here, import libs here. So I'm gonna use IEEE std underscore logic, and it's gonna be 1164 point the dot all. So basically we're gonna use all the things inside this library. Let's start the entity. This is just a comment, so let's do the entity. So the entity is going to be the same as the file name, and we're going to have two inputs and one output. The two inputs is going to be clock and the set, which they're going to be an std underscore logic, and the output is going to be a Q, and it's going to be a simple std underscore. It's going to be, first let's initialize this. It's an input, right? This is an output, so it's going to be an std underscore logic, and it's going to be a vector, of course, since we're going to have feedback register. So it's going to be a vector from 2 down to 0. Okay, we don't need to do the semicolon over there. It's because it's over here. So basically we have this already set up for us. Now we're gonna end the entity. So we already end entity. Right. So now go ahead and do the architecture. The architecture where the magic happens is here. Architecture, I hope I spelled it right. So the architecture. Let's do the architecture. The architecture, I'm gonna name it architecture, and of std. Okay, we don't need the signals. Okay. Basically, we need to put this thing over here. So, and alright, so now we have everything set up. I only need to do a process. So we need an you need a process. The process is gonna identifier for the process. I'm just gonna name it P0, and the sensitive list, I'm gonna do the clock. Also, I'm gonna do the set because the set is an asynchronous signal and the clock is also asynchronous signal, but anything follows the clock is a synchronous signal. So basically, before beginning, we need a few variables. Variable. Okay, I need to spell this right. Okay, let me just check the spelling. Okay, just missed that variable. The variable is gonna be the register. Okay, it's gonna have an std logic vector, and it's gonna be from 2 down to 0. Okay, and the other variable is gonna be a feedback variable. We're gonna see what we're going to do with those two. So basically, we just initialize 2 variables. All right, just gonna do this quickly. All right. So to begin the process, first we are going to check if the set is equal, because the set is the priority, right? It's equal to 0 since it's a low active. Then what we're going to do is simply do the make the register equals to, since it's a variable, you use this what do you call it again, processor or operator, sorry, uses this operator because it's a variable. If it's a signal, then you use this assignment signal to a signal. So this is assignment to a variable. Anyways, you do the register and make the values for the register equals to 0. So I'm gonna use this, and I'm gonna tell everything is gonna be 1, sorry, because we are dealing with a set. So you can use this method, or you can use the other method, which is just basically spelling it out. Sorry, 111, since it's a set. So it's up to you, but I prefer this method because it's much more better. It depends on, it doesn't matter if I change this range, then it's gonna be figuring out how many bits inside this. I'm just gonna set them all to 1. So basically, it's a general format for setting everything inside the reg to 1. So anyways, else if the set is not 0, is 1, basically you're gonna check for the other thing. Else if the rising edge for the clock is from 0 to 1, if that happened, then do this. What are you gonna do? Of course, you're gonna do something awesome. First, I'm gonna set the feedback. The feedback is gonna equal to, the reg. If you look to the design, you're gonna see that it equals to the Q3 XORed with the Q1, right? So the reg2 XORed to the reg0, right? Okay, because we have the feedback already, now we need to change the register. The register is gonna equal right now, it's gonna equal to the feedback, right? This is the shifting part, and concatenated with the reg from 2 down to 1. Okay, you can do it this way, or you can do it in another way, which is sometimes I prefer, is like reg from 2, then concatenate it, also concatenate the reg 1, and you have simply 3 bits inside the reg, which is the feedback, then shifting two bits from the register. So it's also works this way. Anyways, after you finish the if statement, you are going to assign the reg variable to the actual output, to the signal where it's going to be outputted to. So now you have the Q is assigned to the register, which is the reg variable, and we did the all magic is happening to the reg variable. So basically you can't do this thing like for the, you can't do this thing for a simple output, use it as an input also. That's not gonna work out. Anyways, that's why we're defining a variables over here. So now we assign the output, and I think we are done with this architecture. We have the VHDL code written out, and it's done. So let's go ahead and close this and try the test bench. Go ahead and try to compile it first. If it checked, then we are good to go. Yep, it checked. So go ahead, open the test bench, and let's import again the libraries. And let's do the comment first. Import lives, and I'm gonna go ahead and say library IEEE, and I'm gonna use the IEEE.std underscore logic underscore 1164.all. Alright, now what I'm going to do is do the entity. Alright, int entity. Basically this is a comments only. It's just my way of doing things. Alright, now we're gonna have entity over here, which is gonna be yes, that thing, but since it's a test bench, we don't need any ports for the entity. Yeah, I need this to be as an entity. So save this, we have the entity ready for us, and let's do the architecture. If you're still confused what kind of program I'm using, you don't need to, because this is quite complicated to set this kind of thing up. But you can use the default editor for VHDL coding that came with models, and it's all fine. Anyways, continuing on, I'm gonna do the architecture for the test bench. It's gonna be a little bit different over here, the architecture for the test bench, but it's obviously the same from the beginning. Like most of the test bench are exactly the same. What you're doing is that instantiating the chip that you created, which is the chip that you want to test it. I'm gonna show you right now how to do that. Architect, I think I just messed up. Architecture starts here. Let's do the ending. Ends here, wherever. So architecture, I'm gonna name it exper1. Yeah, test bench. I don't need do I need signals? Wait, do I need signals? yes, I do need signals because we are dealing with a test bench. Since we don't have any ports over here, we need to specify what signals we need. So the signals we need is clock. I'm gonna just label it as I as an input, and also I'm gonna use the set as an input. So I'm just gonna make it alone because I also want to initialize them to be equal to 0. Okay, I'm gonna tell you why did I initialize them later, but let's move on right now. Signal, and I'm gonna do the Q and label it as an output, just a label, just a name. Now I'm just gonna go ahead and do the std logic underscore vector because we are testing if the output is gonna be a vector. So vector, and it's gonna be 2 down to 0. I'm gonna do an semicolon, and we have done the variables that we need. There's two types of testing your element. Either instantiating it using the component keyword if you're still remembering it, or just a simple way, an easy way to do it is go inside the begin, do a label for your chip, let's say G1, gate 1, wherever, and do an entity keyword entity and say that the entity you want to instantiate it is under the work, and the name of the entity is linear shift register, and the architecture for it is going to be architecture, just like that. And now you go ahead and port map it just exactly like we usually do. So the first signal is the clock, second signal is the set, the third signal is the Q output. Just do that. You have the signal ready for you. So save this. Now let's do the clock assignment because it's an input, 2 inputs we have, right? So clock assignment, I'm gonna do a little bit of magic thing because I instantiated to 0, right? I'm gonna tell it to be, and another thing, since it's not specified as an input or output, that means I can use it in both ways, here or here, so it will not give you an compilation error or any error if you did that. So basically I'm gonna go ahead and use the clock, and I'm gonna assign it, since it's initially have a 0 value inside it, so I'm gonna assign it to not clock. And I'm not gonna assign it immediately, I'm gonna assign it after a specific delay, which is 5 nanoseconds. So basically what's gonna happen is each 5 nanosecond is gonna be inverted, so that's gonna you're gonna have a clock signal. Okay, so this is what you're gonna have. So basically every 5 nanoseconds is gonna be inverted. Easy as that. So you have the clock already ready for you. Now since we have an active low, and it's initially active low set, and it's initially activated to 0, then the output is gonna always be what? It's gonna be 1, since the logic says so. So to change the set, and I'm just gonna go ahead and assign it to 1, but not immediately. I'm gonna assign it after a specific delay. You can make it 5 nanoseconds. I'm gonna just make it 10 nanoseconds for fun. It depends on how many nanoseconds you need. Anyways, in the first 10 nanoseconds, the output is gonna be 1. All right, since it's gonna have the logic value of 0. Okay, that should be logic value. Don't make this if you kept it like this, it's gonna assume that you're assigning not a logic value. It's gonna assume that you're assigning a 0, which is 0. Basically you're assigning a logic value of 0, not 0. So use those. Alright, I'm gonna save this, and I think it is all set up to go. And let's save this thing out and just close this. You don't need it anymore. Just try to compile it and hope for good. If it checked, then we are all set. Alright, we are all set. Go ahead and start simulation. Start simulation. Use the workspace because it's under the workspace. Press the test bench. We created it, and some magic is gonna happen. I'm just gonna go ahead and reset my layout because I just changed it a little bit. So basically now I have my layout reset as a default layout. I'm just gonna click the inputs and the outputs that we need to test and just add them to the wave. So just gonna close these. I don't need them right now. If you close a lot of windows, then you can just go ahead to layout and reset, and then they will pop up again. So I don't mind to just close them. So I'm just gonna have 100 nanoseconds for the whole thing. So I'm just changing this to nanosecond and just gonna press run, or you just can use the run from here, but I'm just gonna do it the traditional way we used to do it. Just press here and you're gonna get your output. Basically it's zoomed in way in, so I'm gonna go ahead and zoom out and check the output. So yes, the output is gonna go from 111. Okay, if you want to see it in a waveform, you just press this plus and you're just gonna expand the vector output. So basically this is the first element inside the vector, second, so on. So basically right now we have all 1 as the set is 0. Once the set changes, the output will change. If the set is 1, then it's gonna all change to, and according to the clock, when the clock clicks, then the output is gonna all change to 0, 1, 0, and so on, and it's gonna repeat once it reaches 1, 1, 0. And just so you know, mine is this is the high most significant bit, and this is the low anyways, you got my idea. I forgot the naming conventions. Anyways, so basically now it's cycling. If I just press again, you're just gonna see the cycle going on. So it's gonna be infinitely cycling through those numbers, which actually what's the question says. So I think that's all what we need, and this is the full everything you need for the first question. So if anything you didn't understand or you find it difficult, just drop me a comment, or just drop me send me a message, or ask me during class or stuff like that. I don't mind. If I'm busy, then I'm gonna tell you I'm busy. So anyways, I hope you guys viewed this as a good reference for you, and okay, see you in the next video where I'm gonna be talking about the state machine, probably soon. So when I finish it, because I still have a little bit of problem in the test bench on it, but it's okay. I think I'm gonna ask the lecturer about it, and everything is gonna be fine. So anyways, hope you guys found this useful, and peace out, enjoy life, and bye.